Hello and welcome to some slides about a concept called Boolean Algebra. It is surprisingly stuff that you already know, it's just everything looks weird and different. But really, this is just logic all over again, okay? So let's get on into it. What in the world is this thing called Boolean Algebra? Well, if you go to the definition, it's a set of rules and operations for working with variables whose values are 0 or 1. So that's where the logic comes into play. So 0 is false, and 1 is true. This was like logic before logic was invented. We had Boolean algebra, okay? So everything just looks a bit different. 0 is false, 1 is true. Instead of and, we say multiplication. Instead of or, we say addition. And instead of not, we use complement, like for set theory. We use a bar, okay? So that's really it. Just replace everything, and you know this already, okay? Replace all those symbols with these other ones. Alright, we have some other terms that we'll get into. A literal, that is a Boolean variable or its complement. It's like a very simple thing in a Boolean algebra statement is called a literal. Okay, so it's just a variable or the complement of that literal. Okay, and then we say that a min term, which is another weird word, it's when you are making a product of any number of literals. Okay, so literals are variables or their complements, and you're allowed to take a product of as many of those as you want. Potentially just one, potentially multiple, more than two. That's totally fine. Okay, so it's you anding together either some variables or some negated variables. Okay, that's all a min term is, and there are reasons that we like these, and we'll get into those. Okay, so here's your first meme. Enjoy it while I take a look at my notes and see what I want to talk about. Yeah, so let me actually just go back here and go more in detail in these operations. So like, the reason they chose the multiplication sign for and is because like 1 times 0 really is 0, right? Isn't that cool? Which represents the idea that true anded with false is in fact false. That's kind of why they chose that one. Plus doesn't make as much sense, unfortunately, but it makes enough sense, right? 1 plus 0. Hey, that is 1 in actual arithmetic. 1 plus 1, though, is not equal to 1 in actual arithmetic, but it is in Boolean algebra, because true ORed with true is true, right? And then you have your complement, so 0 complement is false negated. That's true, right? That's 1. And then, yeah, a min term can be anything, so it can be as many literals as you want to multiply together. So x times y times z bar times x bar times just normal z. Doesn't matter. So it's a product of literals. Okay? So with that, let's talk about gates and circuits. Because you can build cool stuff using these operations, and we could form them as circuits and pretend that we're building like actual hardware out of them. Okay, so yeah, everything in Boolean algebra is able to become actual hardware. You can make circuits that perform these logical operations. Okay, and the individual pieces of those circuits are called logic gates. Those perform a single particular Boolean operation. Okay, which is quite nice. So like, every logic gate takes some stuff coming in on a wire, like a 1 and a 0 maybe, and here is your gate that might perform like the OR operation, and then it's going to output 1. That's how we're going to read these diagrams. Okay, so you got your inputs and your output. And you can make cool stuff, like you can draw these things. There are plenty of places on the internet that help you do it, like some of these websites if you want to look at their simulators. Whee! Well, that's taking forever to load. Let's try this one. All these gates we can drag out here and put stuff coming into them and make them bigger. Things like that. So play around with this once I've taught you about this stuff. It's cool, and we'll come back to it then. Okay? So we're going to learn about each of those different kinds of circuits, and it's really just a pictorial form of a Boolean expression. Okay? So here are the main gates that I care about you learning. Okay? Bill Gates is, of course, a valid logic gate. So you will see these three. Okay, these three can make every other gate in some combination. Okay, there are fancier ones, but these are the ones we mostly care about. Okay, the ones that we know and love. So this first one is called the AND gate, and it performs the AND operation on its two input wires. So it's going to multiply them together if we're working in Boolean operation land. Okay, Boolean algebra land. And the symbols are always like this. They're always drawn like this. This kind of looks like that that bullet character from Super Mario Brothers. So you can remember that. And so that does the AND operation. That's the AND gate. And this one's the OR gate. Very similar to AND, but kind of cut out there and more curvy and connects at a point on the right side there. So it takes two input wires and outputs their sum, which is the OR operation on them. Okay? And then finally we have a inverter. Sometimes I call this a NOT gate as well. Also correct to call it that. And it only takes one thing, right? Because it only has one thing to negate, right? Outputs the negation of x, or x complement if you're using Boolean algebra. Okay? And so to help you understand future gates that are fancier, that have similar symbols, I want you to think of the negation happening at the dot right there. Okay? Think that the negation happens right there at the dot, and this triangle is just kind of like passing it through or something. That'll help you read future diagrams. Okay? So those are our gates, and let's try these out. Okay? So take a look, and I'll also try this out in one of those simulators just for fun. But see if you can figure out what the output of this gate on the right is. Here's the output over here. What the output will be when x is 1, y is 0, and z is 1. So that's a question that we can ask. Maybe if you're feeling like it, try it yourself right now. See if you can come up with it. And we also want to be able to tell, like, what is the Boolean formula that this circuit is computing? Like, what is it really outputting over here in terms of the inputs x, y, and z? Yeah? That's the kind of stuff we want to be able to ask. So with that, let's see what happens. So if x is 1, y is 0, z is 1, what's going to happen here? It's going to, well, it's going to take 0 and 1, OR them together. That's an OR gate, right? OR gate, AND gate, AND gate, and these two are NOT gates, or inverters. So ORing together, x and y, that gives us, well, whatever they are, x plus y, right, in Boolean algebra land. Interesting, interesting. And similarly for these, this is negating whatever's coming out of this wire. This is a cute way of indicating that you're hopping over another wire, not touching it. So this is still x down here. And here's us negating x. So this holds x complement. And this one holds z complement for the same reason. And then it ANDs them together. So this is x complement times, right, z complement, using that new notation. And then finally we AND together this guy, and that is our output. Isn't that quite nice? So at the end here we have x plus y multiplied by x bar multiplied by, not y, sorry, multiplied by z bar. Okay? So that's actually the answer to the second question. What's the Boolean formula that the circuit computes? Well, it's x plus y times x bar times z bar, right? Really it's like this, but multiplication and operations are associative, so I can get rid of these parentheses. And this is, of course, equivalent to the notation that we know already, right? X ORed with y, ANDed with not x, ANDed with not z, right? And so now we can just, well, we could have just ran this with ones and zeros, but this is more general, right? It doesn't matter what it was, that's always the right answer. So let's plug ones and zeros into this. This was computing, well, x was 1 plus y is 0 times x bar, which is going to be 1 negated, that makes 0, right? I can draw it like this, times 1 bar, right? times z negated, right, which is 1 bar again. So let's calculate that. That is going to be 1 plus 0, that's 1, true, ORed with false is still true. True, ANDed with not 1, or complement of 1, so 0 times 0. So we're ANDing with false a few times, and that is unfortunately going to be false. Okay, so we end up with 0 at the end of that. Okay, hopefully that made enough sense. And we can try this in the simulator too, because why not? So it looks like this one loaded faster last time, so let's go there and let's build this. Let's build this circuit because we can. So we need an OR gate. We need 3 inputs first of all. So we're going to need 3 inputs as light switches. And that'll be X, Y, and Z. And then we need an output, a 1 or 0. That'll be just the light bulb lighting up if it's a 1 and not lighting up if it's a 0. And then I need some NOT gates, right? Some NOT gates, also called inverters. I needed an OR gate and 2 AND gates. So there's my OR. And 2 of these AND gates. Isn't that neat? So yeah, all I have to do is hook these up properly. So we're taking, it's 1, 0, and 1, so I think that off is 0, right? So now they're set properly. So we're taking X and Y, giving them to an OR gate, like this. And then we're taking X and Z and giving them to both of those NOT gates. So we're doing that and that. And then we're ANDing together this result here. And then we're taking the OR and that ANDed result. And that is our output. Yay. And it would seem that, oh sorry, the down position is on? Weird. Okay, that's fine. That means 1, 0, 1 means 1, 0, 1. And oh man, it's off. Isn't that nice? So how do we make it on? It looks like, which one was controlling it? Well, it was some combination of these guys. I had it once. It was just this one, right? If you made it 0, 1, 0, it seems, this ends up being true, because you're ANDing together these two things, which would have been both 0 made 1. Okay, that makes sense. Cool. Nice. So maybe that's the only way to do it. But that is, this was our original idea. Okay? So, isn't that fun? It's kind of a graphical way of seeing how Boolean formulas are interacting with their values. Okay, now it's your turn to try. So try and draw the circuit diagram for this Boolean expression, and watch out for this complement. This is taking the complement of W plus Z, okay? Complement after doing this. It's not complement W plus complement Z. That complement's going over the whole thing, okay? So just notice that, and that will help you do it. And then also evaluate when X and Y are 1 and W and Z are 0. All right, assuming you gave that a try, let's talk about it. Okay. Oops. Here we are. So this is an AND, right? I mean, first of all, we have 4 variables, 4 inputs, X, Y, Z, and W, and they're leading into some stuff, right? We need to AND together first, X and Y negated, so we have to negate using a NOT gate or an inverter, Y, and then take it with X, put it into an AND gate, which looks like that bullet from Super Mario Brothers. And so now this is holding, this wire is holding X, Y bar, or X times Y bar, yeah? And now let's work with this side. So we need to take Z and AND it together with W plus Z negated. W plus Z complement. So I guess the first thing we need to do is find W plus Z, right? So let's do that with an OR gate, right? And the order doesn't matter. Z plus W is W plus Z. It's commutative, right? So this is W plus Z. And then I want to negate that. I need to take the complement of that, right? So now this is W plus Z complement. And now I want to AND it with Z. again, order doesn't matter. So let's have an AND gate, and this one can be on top. And we'll take Z, hop over that wire, and bring it up into here too. Yeah? So this is now holding Z times W plus Z, all of that complemented. See how that's working? And then finally we can bring it back together with the other side with an OR gate. And so finally, we have our final output, which is holding xy bar, right, plus Z times W plus Z, all complemented. Yay. So, okay, with that, evaluate the expression when x is 1 and y is 1 and w and z are both 0. So that is going to be, if I just replace all of these, let's do it together. So x is 1, y is 1, complement, plus z is 0 times w plus z, so 0 plus 0 complemented. Yay. So this is going to be true ANDed with false, right? So that's false. ORed with, well, 0 ANDed with 0 plus 0, that's still 0. Complemented is 1, so times 1, which is still, I mean, that's false ANDed with true, so that's again false. So false ORed with false. Oh man, that is false. So it's 0 at the end. But it's just new syntax, so getting used to that. Okay? Definitely yell at me if you have any questions about this, but this is just logic all over again in a new form. Okay? Another joke for you that you can now understand. So, let's get back to, like, I gave you that definition of min terms. Let's understand where that's coming from. So we have some forms that we would like to get our Boolean algebra expressions into, if at all possible. One is very nice. Well, actually, both of these are very nice for different reasons. So, wouldn't it be nice, most of the time it is, to get a formula into a disjunctive normal form? Okay, that's what it's called. Get it into disjunctive normal form, or DNF. That's when you have made a sum of products of literals. Okay, so you have a bunch of products and you're summing them together, so the outermost operation is disjunction. That's why it's called disjunctive normal form. It's a disjunction of conjunctions. Sorry for all the Latin roots. So here are some examples of DNF, or just one, I guess. So it's just a sum of products, or a bunch of ORs of ANDed stuff. So x and, like, not y, and z, ORed with, like, w, or, like, here's one thing ANDed together. This is a better way to explain it. Here's another thing ANDed together, just one thing. Here's another thing that's ANDed with some other stuff. And if this is in DNF, that means I'm ORing all this stuff together, all of these conjunctions. I'm disjuncting all of them, okay? So that's DNF, and if we translated this to Boolean algebra, it's x, y bar, z plus w plus p q bar. You see that? I can also introduce those time symbols if you'd like, but it's a sum of products. I hope you see that. So that's DNF. It's useful. Conjunctive normal form is the exact opposite. It's when you take a product of sums of literals, or you like normalize your formula so that it becomes a product of sums of literals. Okay? So the outermost operation is a conjunction, like an AND operation. So that's why it's called conjunctive normal form. It's a conjunction of disjunctions. Okay? So sorry about that. So if I swap all these, it becomes a non-equivalent thing, but it becomes CNF. So let's say I have x ORed with not y, ORed with z, and w, and I have p ORed with not q, right? That is going to be CNF if I then and them on the outside together with each other. Yeah? That's the key. Let's do another one. Like, let's take P or Q. Let's take X or not Y. Let's take Z or W. And so it's a bunch of sums. I need to take the product of those, so and them all together. Yeah? And that is equivalent to, in Boolean algebra land, P times Q plus X times Y bar plus Z times W. You see that? So it is a, oh sorry, I did that completely backwards. I'm too concentrated on DNF. It's or is plus P plus Q times X plus Y bar times Z plus W, excuse me. So it is a product of sums. That's what CNF is. Okie dokie. And the goal for these DNF and CNF, it's pretty to look at when it's in this form. It also helps you read off answers sometimes for like when it's true or when it's false. So usually, well, it's always possible to transform a formula into DNF or CNF. It's always possible, and that helps you get a grip on what you're trying to talk about. Because like one day you might have some big long expression like X times Y plus, like, I don't know, Z times W plus P, all of that complemented, times with Q and all of that complemented as well. That just, that gets really hairy really quickly, and nobody likes that. So we don't like this. Too complicated. We'd like to transform it into DNF or CNF. Okay, there's ways to do that. So that is, that's the idea of those. And yeah, it's going to be helpful to get things into that form. All right, so I'm going to force you to use either DNF or CNF right now. Remember how to do this. Find a circuit that computes this function on the right, given this input-output table. Do you remember how to do that? Like this was the question mark from before, from the logic slides. I taught you one of these secretly, and that lets you read off the answer, didn't it? So it is useful. You just didn't know the term before. All right, so let's see what this is. So get that as a formula, and then you can use that to make a circuit for it. Okay. So what is F? What is F? What should it be? And the trick that I showed you was find all of the true cases, right? Here's a true case, here's a true case, and then express that, right? So what was true here? Well, X was false, not X, and Y was false, not Y. So that's one part. And then we had, this was true, right? So X was true, and Y was false, so X and not Y. And we wanted it to be true when either of them were true. And what do you know? Which one is this? That is DNF. We got into DNF, disjunctive normal form. That lets you immediately find a formula for a truth table. Isn't that nice to see when something's true? It's like, okay, it's true in this case, and it's true in this case. Cool. So in Boolean algebra, that's going to become X bar times Y bar plus X times Y bar. And yeah, that's about it. We can draw a circuit now from either of these. So we have X and Y as our variables. Do I have enough room is the main question. I need to do several things with these guys. I need to negate them both, right? I need to negate them both. So might as well do that. And then I need to AND those together. So here's an AND. So this is right here, X bar and Y bar. And what else? I need to OR that with X and Y bar. So let's take this AND right here. This is just normal X. Hop over this, please. Let's get that on the right side of the AND sign. So there we go. So that's just x, and then we want to take y bar again, so I'll just take another version of this right there, and this will give me x and y bar. And now I want to take both of those and OR them together using an OR gate. So there I am using my OR gate, and now I have the correct output. I have, let's see here, x times y, both of those barred first, plus x times y bar. Yay. Did you get that? Definitely yell at me if you have any questions about this. But it's just all logic all over again, just some new symbols, some new notation. Nothing too much, right? We also have the same laws from logic for Boolean algebra, of course. It's the same thing under the hood, it just looks different, right? Here is your associative law, using plus instead of or. Here's your associative law for times instead of and, right? No difference. You can kind of see why it's called distributive law now, because it's like, oh, at least for this one. This one is the normal one that makes sense for normal math, right? You can distribute the x over the y, multiplication over addition. Cool. You see why I call it a 1. X times 1, oh yeah, that is x. X times 0, that is 0. X plus 0, that is x. This one makes no sense in arithmetic, but it does in Boolean algebra. Okay? So, yeah. Here's what De Morgan's law looks like. That looks a bit odd for each of those operations, whichever one's on the inside. And yeah, all of these are the same. They just look a bit different. Like double negation becomes double complement, right? So you can use these in the same way you used them before. So I want you to give them a try. So use the laws to show that this fancy expression is the same as this one. And name all the rules that you use, please. Okay? So starting from up here, x plus x bar times y, all of that barred. How can you move down here to get to just x bar times y bar? Okay? So give that a try using this table. And then we'll come back and do it together. So I think normally the right idea for logic was always push that negation inward. This is negating a big long thing. Let's push it inward with De Morgan's, right? So we've got an OR that we are negating over, yeah? So using De Morgan's, it's this one. It becomes an and of each little thing negated, okay? Each little thing complemented individually. So this becomes x bar times this thing barred, right? So x bar times y barred. Yes? Does that make sense? That's De Morgan. And now let's keep pushing that negation that's not on a single term inwards. Okay, so this is another De Morgan we can use right here. So this one stays, and then this becomes, the and becomes an or, right? So, and we distribute that complement. So x complement complement, ORed with y complement. That's another De Morgan. And now we're off to the races. Okay, so what can we get rid of here? We have a double negation. We can get rid of that. That's the double negation law. So x bar times x plus y bar is what it becomes. Do I call it double negation or double complement? It's really double complement. Let's be precise. And then, like, what do we do here? We kind of have to get the ORs to go away. Like, we want to just and. So maybe we could distribute that multiplication over addition. We could use this one. So I think that's the way to go here. So let's distribute using the distributive law. That's going to be x bar times x plus x bar times y bar. So that's distributive law. And this is actually essentially the answer because we want to keep this and we want this to go away. Does it go away? It's gonna because of, which one was it? Was it anded together? Yeah. It was this thing, complement law. If I have anything and I and it with its complement, I get false. I get 0. So this becomes 0 ORed with x bar y bar. That's the complement law. And let's just confirm I'm doing that right. Technically, if we wanted to be extra precise, the thing that is barred must be on the right. So if we wanted to get super fancy, we could use a commutative law first to make sure that that is true. So let's just, why not? This is class. Let's spell it out. If this was a homework, I could understand that you wanted to do this, and you can just omit this part, but technically it's required to use this. X bar times y bar. This is commutative law. And then you can apply the complement law and not worry. Now I can get rid of that 0, because 0 ordered with anything is that thing, but I need it on the right, don't I? So let's use another commutative law. X bar y bar plus 0. So another commutative law. Use. And then finally, x times y, both barred, is what we end up, because this 0 goes away thanks to the identity law. That's the one. Yay. Hopefully that makes enough sense. It's just proofs all over again, or those logical rules used all over again. Okay? So, yeah, 2 more questions for you, and that'll be it for this lecture. Let's see how we're doing. Yeah, plenty of time. So, let's see here. Here's what I want you to do. So for this table, again, kind of like this last one, what I'd like you to do is give an expression that is a sum of minterms, right? Sum of minterms. And so what does that mean? What's a minterm? Product of literals. Oh, okay, so I want you to give a sum of products of literals, that is DNF. I want you to write DNF, okay? Please do that, and make it be the same as this function f right here, okay? So what is this? See if you can calculate that. Write a DNF formula for it in Boolean Algebra. Alright, so again, the trick is always to just pick out what's true. Here we go. And so this is true when x is false and y is false. So how do we make that into a true statement that gives true back when x is false and y is false? Well, you just take them both and negate them. So x complement ANDed with y complement. Okay? Or multiplied with y complement, we say. So that's the first part. That was this. That'll make a 1 there in that case. And then we also want a 1 when x and y are both 1, so when they're both true. So how do we make a formula that is true when x and y are both true? Well, we just AND together x and y in that case. Okay? And so we wanted a 1 in each of those spots, right? So again, we'll just OR together that result, because this one gives me the 1 here, this one gives me the 1 here, and together they give me the final table that I cared about. Okay? Does that make sense? So, just for free, just based on the way I taught you before, we ended up with DNF, which is super nice. We ended up with disjunctive normal form. So it's a sum of products. And another way to talk about a bunch of products of things is a minterm, a product of variables or complements of variables. Okay? So it's a nice thing to want to get into, DNF, isn't it? So also, I think you might notice that this is another way of writing that biconditional, right? Because it's only true if they agree on each other. So that's the if and only if operation from logic. So if we were allowed to use that, maybe we could simplify this a little bit. But with and or not, that's what we get. Okay? So that's the first one. Hopefully that made enough sense. And now let me give you one last one to try. Alright, so use the laws again. So I want you to convert this Boolean expression to DNF, because you can always go there. You can always go to DNF or CNF. It might take a lot of effort though, unfortunately. Okay? So try this and name every law that you use. Okay? That's important. Because it has to be by the book. It has to be equivalent. Okay? So, one good reason, of course, is to get it into DNF is to be able to write a truth table, to be able to read off, like, okay, it's true here, in this case, and in this case. That is exactly what DNF gives you. It lets you read off immediately when, under which conditions on those variables is the formula going to give back true. Okay? So, first thing I want you to notice is this is not two separate bars. It is a single bar. So it is and first, then bar. Okay? And remember that DNF, we need to do a disjunction of conjunction. So a plus of timeses, if you will. Yeah? So keep that in mind. And let me just spell this out. Oops. Down here as well. So notice that this is x times y barred altogether and not x bar times y bar. Completely separate things, right? So keep that in mind. All right, so let's see what needs to happen here. So give it a try, assuming you're back now and you gave it a try. Let's see what we have here. So I'll just put the times there for fun. So this is what we start with, right? And then we're multiplying that by x plus y, and all of that is barred as well. Okay? Because we want min terms, right? Essentially, at the end of the day, we need to push that negation. Anytime a negation is not immediately over a variable, we need to push it inwards, as usual. So let's do that for both of these. We're going to have to use 2 De Morgans, I think. Okay? So let's make that happen and see where we get based on that. So let's do a De Morgan on this one. So that becomes x bar ORed with y bar times whatever was over here, plus y, all barred. So that was 1 De Morgan. And then let's do it again for this one. Okay? So we keep what was here, and then we multiply with this. This OR becomes an AND now, right? So we have x bar ANDed with y bar. Let's make sure that is what it looks like. Yes. So that's another application of De Morgan's rule in Boolean algebra land. And now what? What can we do here? Let's see. What would we like to do? We'd like to get all of the timeses by themselves. We'd like to have the plus at the outermost level. So I think the trick is going to be distribute all of this into each of these sides. Does that make sense? If we use the distributive law, then we could have the plus be the outermost operation. We could distribute that inwards. Yeah? That would be us using I want to say this one, yeah, because then plus becomes the outermost operation, and then the x in this case is just a big long conglomeration of other things. It doesn't have to be a single variable. But in order to use the distributive law, apparently we need it on the left, so let's practice using our commutative law one more time. So let's get the thing that we want to distribute on the left side. So that's going to be x bar times y bar times x bar plus y bar. That is commutative law. And now we can distribute. Okay, so let's distribute that inwards to both sides. And that's just how it works, right? So we take what was on the left and bring it to both sides, xy plus xz. Here we go. So all of this times x bar plus all of that times y bar. Okay? Here we go. X bar times y bar one time times x bar plus x bar times y bar times the y bar over here. You see how that's distributing? And because of the associative law for and, or multiplication, we could then remove any of these parentheses. They don't really matter at that point, and I'll be lazy and do that now. So technically, this is fine. And this was the distributive law, right? Let's write that. Dist law. So, notice that this is an answer. This is DNF now. We have made it a sum of minterms, a conjunction, or a disjunction of conjunctions. It's hard to remember. So we could technically stop here, but let's not, because we can do better than this. Let's simplify this. It's totally capable of simplification, right? I don't need 2 x bars on one side. That's silly. I don't need 2 y bars. That's also silly. Okay? So, if I have 2 things together, the same thing, where is that? Up here, idempotent laws. And we're using it for multiplication, right? If I have the same thing twice, it's just one of those things, right? I don't need it twice. So it looks like I need to get them next to each other in order to apply the rule. So maybe we can do that. X bar times y bar plus x bar times y bar times y bar. So on this side, it's already fine. So that was a commutative law again. And now I can make those 1 again, right? I could make those just fine with an idempotent law. So this becomes x bar times y bar plus x bar times y bar. And that was 2 applications of the idempotent law. If you want to get into more Latin roots, this means same, this means power. So writing it twice had the same power as writing it once. Okay? In case you care. So yeah, that is a much simpler form of this. And you know what? We can do it all over again, because here we have it ORed with itself twice. Another idempotent law, x bar times y bar, another idempotent law. Crazy. So this is the final form, DNF. Okay, so yay. Does that make sense? So this is where we could have stopped. We also could have stopped here, but yeah, we could keep going. So yeah, this is DNF. In a nutshell, it is useful because you can tell immediately, like, okay, it's true when x is false and y is false, and that's the only time. Okay, that's my formula. Much simpler than trying to read that off of this. Yeah. So yeah, that's everything that I want to talk about for this lecture. We'll come back and do more cool stuff. We'll learn about fancier circuits next time as well. NAND and NOR, if you've heard of those. And yeah, but that'll wait until the next lecture, so I will see you then.